Hello, my name is Benjamin Staugaard from the SDU Center for Energy Informatics in Denmark. And in this presentation, I'll introduce our work on geolocation-based privacy-aware indoor climate data access and control in IoT-enabled smart buildings. This research is a collaboration between SDU in Denmark and Uniten in Malaysia, and it is a part of the IoT Building Cloud, a low-cost, intelligent energy management system for commercial and public buildings initiative, and the IEA EBC Annex 96 Grid Integrated Control of Buildings. Buildings account for roughly 30% of global energy consumption, and existing buildings in particular present major opportunities for efficiency improvements. Retrofitting with IoT sensors enables fine-grained monitoring, data-driven control, and better thermal comfort. However, as installations expand, they introduce a parallel challenge. Many existing systems still rely on static access control and continuous user tracking. This creates tension with GDPR principles, especially the data minimization and purpose limitation, because indoor climate data can implicitly reveal occupancy patterns. Our goal is to provide operational intelligence without requiring users to be continuously monitored, and without relying on detailed pre-existing floor plans or full BIM models or CAD models for that instance. Instead, we let the deployment of the devices that we retrofit themselves define the spatial context. This leads to the central problem that we address. So how do we enable access to indoor climate data and enable control actions such as heating or ventilation while ensuring privacy preservation? Furthermore, how do we authenticate presence without storing or transmitting continuous location traces? And how can we support buildings where no digital floor plans exist, which is common in retrofit scenarios? The solution that we propose is a dynamic geofence constructed automatically during the installation and evaluated locally on user devices, ensuring privacy by design. Our contributions consist of 4 elements listed here on this slide. So for the first bullet point, we provide a dynamic geofence system that is derived directly from GPS metadata collected during the installation. So it is the installer that collects this GPS information, and this is done automatically. Second, all geofence evaluations should occur locally on the user's mobile device. In this way, the user's coordinates are never shared across the wire or sent to a backend somewhere, which would violate GDPR. Thirdly, we propose a layered access control design covering all of the stakeholders in the system. So that is installers, managers, authenticated users, and temporary guests. And finally, we integrate geofence-driven events with building control routines, and this allows us to enable anticipatory thermal preconditioning based on user proximity. So on this diagram, we see a system overview of the deployed system, or the deployed systems, I should say. This diagram summarizes the end-to-end architecture. The backend is implemented in Java-Spring with MongoDB, handling all device and spatial metadata. Then we have an Angular front-end dashboard, and this provides 2D and 3D visualizations. For the 2D visualizations, we use Leaflet and OpenStreetMap. And for the 3D visualizations, we use Three.js. We also have 2 Flutter mobile applications. So one is for installation, and the installation app is, of course, used by the installers when they retrofit the building with new devices using a smart QR code-based installation process. And then we also have the user app. So this is used both by authenticated users and also by guest users. And it allows them to gain insight into the climate data that is collected in in an authenticated manner, so guests can only have a live view, and authenticated users can also get historical information. This workflow shows how spatial boundaries are formed. So technicians or installers register each device by scanning a QR code in the room. At the moment of the scan, the installation app records the current GPS position of the installer's mobile phone, and the approximate position is enough for this purpose. The next step is that all points are stored in the MongoDB database, and this forms a growing collection of spatial metadata. As we add more devices, the backend computes this convex hull, and this approximates the building's footprint. And you can see on the image here, we have collected a bunch of GPS points, and these have been visualized on the 2D OpenStreetMap, and this is the convex hull that then approximates the building's footprint. So this process in its entirety requires no floor plans and no CAD models and no manual mapping. Basically, the user or the installer in this case simply scans the devices and a GPS coordinate is sent, and then the system builds this convex hull. Moving on to the data access model. Access to the indoor climate data is determined both by user role and physical proximity. And this diagram here depicts this. So authenticated users get full access to shared spaces and assigned spaces inside the geofence, but they may only receive limited or aggregated data when they are outside. So for example, in the case of an authenticated user, if they have an assigned office, then they can still access the full data of that office when they are outside the geofence. But for shared spaces, they can no longer access historical data. In turn, guests can scan room QR codes for temporary access to live readings only, so no historical data. And they never receive this historical data, and the access that they have expires automatically. All geofence checks for authenticated users and also for the guest users occur on device, so the users do not have to transmit their GPS position to the backend for this to work. And this satisfies the GDPR principles by ensuring that presence is demonstrated voluntarily rather than tracked. Beyond data access, these geofence events also allow various control actions. So when the mobile app detects a geofence crossing, it sends an event to the backend. And this event can then allow the backend to trigger, for example, anticipatory heating or ventilation or other climate routines that have been configured. In our implementation, we demonstrated anticipatory thermal preconditioning, and this means that the room begins warming shortly after we arrive or trigger the geofence. So the office is nice and warm during the winter. And this in its entirety creates a more dynamic and privacy-aware alternative to traditional occupancy sensing. Moving on to the case studies. So our first case study is the library at the University Tenaga Nasional in Malaysia. And this is an 18,000 square meter building with approximately 248 sensors and 21 gateways installed across 80 rooms across around 5 or 6 floors. So although this deployment wasn't configured by us, it was configured by another team on site in Malaysia. The system correctly clustered the geodata into separate geofences and visualized them on the dashboard. So this is what you can see here on the image, that we have 2 separate geofences because the installation started in the university building, and then they started installing in some of their other buildings, and this building has its own geofence. And this would work for all the other buildings as well. So in conclusion, this validated that the system could scale to large infrastructure and also multi-building sites. Our second case study is the Mærsk Mc-Kinney Møller Institute at SDU in Denmark. This is our own office building that we used as a test site. This building is around 2,500 square meters, and we installed 297 sensors and around 13 gateways across 85 rooms across 2 floors. So what differs here is that instead of the 2D visualization, we have the 3D geofence extrusion, and we have the BIM model of our office building. So in this installation, we actually visualize the system using that BIM model. And this also allows us to see how the configured installation looks in 3D with the geofence in 3 dimensions. We also tested the real-time thermal preconditioning, and this was triggered by geofence entry events. So when we arrived in the morning and left later on the day, the offices were either heating or cooling again. Moving on to the results. So we achieved accurate geofence construction in both 2D and 3D. Access control worked reliably for both authenticated users and temporary guests, and the geofence-driven control triggers fired consistently without requiring continuous tracking when the app was open. We also identified some limitations, for example, background execution constraints on some mobile OSs. So if resources are limited or battery is low, sometimes the routines do not trigger. And this is something that we have to look into. The convex hull does not do concave buildings or concave building geometries. So this is something that we can improve in further iterations. And finally, the DB scan sensitivity threshold has to be tweaked for some buildings to get good results with multiple geofences close together. So to conclude, we have demonstrated a working geolocation-based privacy-aware access and control framework for smart buildings. It eliminates the need for floor plans, it avoids continuous user tracking, and supports dynamic role-based access governance. Some of the future directions include adaptive clustering without predefined parameters, a more granular room-level geofencing, and deeper integration with control systems. And we would also like to benchmark this geofence-driven control approach against the conventional occupancy sensing. Thank you for your attention. If you would like to continue the discussion or explore potential collaborations, you're welcome to contact me at the email on this slide.